Okay, so let's start off. Let's get our homework today was create a procedure for writing something to the screen, right? Okay, so we took our generic hello world program. So let's just do a quick 8086 hello world. Oh, that one already kind of does the assignment. This one's good. So I'm gonna, is this like an image? It is an image. Okay, that's fine. We'll just use that one. Okay. It's not that many lines to type. It'll be good practice. Because we want to bring in a data segment. Oh, actually, this will be good to introduce this offset command anyways. Okay, let me just do one more search. 8086, hello world. Oh, well, that one runs anyways. Okay, so last time we started talking about variables, right? So possibly throwing things in parameters, so having our named parameters inside of variables, and those go inside of the data segment. And we also looked at a register called DS, which is a pointer to the data segment. We talked quite a bit about this idea of an offset, right? So we were looking at what that top of the, what gets pushed onto the stack upon calling a procedure, and that is a pointer. That is an offset off the base address of the code segment, where the next line of code should continue when we have a function gets returned. Okay, so we talked about offsets, and we're going to introduce a new keyword today called offset, and we'll see that here in a few minutes. But what I'm going to do is let's gut at least some of this. I'm going to leave my add nums proc down there, and let me just steal some of this code. Beautiful. Just, you really can't beat that. Just can't beat it. What happened?
Shift it over. No, but see, no.
Oh, I get it.
Oh.
Nailed it. Oh, so the other one probably was okay. Okay. Leave that back here. We want to do this probably without the offset initially, so I can introduce offset to you. We'll steal that code for a second. Oh, actually, we'll just go with it. Okay, so I'm going to get rid of our parameters. Well, we'll leave it for now. It's not going to be a big deal. All right, so here is our typical hello world program. So this first thing is the function to display a string. All right, and this is probably the DOS command for it. And I have 2 moves here. All right, so we need to go ahead and define a variable. We talked about variables last time. So inside here in the data section, where's our data? Oh yeah, that's the picture version of that. So I'm going to add another variable in here. In fact, let's just get rid of these other ones. All right, so we have a variable named message that's of type data byte, and we're setting it equal to hello world. This is end of string character in 8086. A couple different ways you could have defined this. If you remember back to the original Linux version of this hello world, if I do hello world assembly Linux, this is kind of the go-to example I usually use. And notice in the data section down here, we have a message, and then we have the length of that message. Okay, so we can use these, this guy just like that as well. All right, but we'll follow this other example. It accomplishes the same thing. In fact, actually, the other example will allow us to just pass 1 parameter instead of 2, which is fine. All right, so let's go back here. So I have a single variable that is my string hello world. Okay, so then in our code section, we have our procedure called blah, which we defined last time. And we're effectively loading some things into some registers. All right, so what are we loading into registers? We're loading into AH, the function that knows how to display a string. We're loading into DX, the offset of our message string that's terminated with the @ symbol. So this introduces this new keyword that we were gonna introduce today anyways, called offset. Let me compare that to what we had here in this Java one, or I'm sorry, in the Linux version of assembly. So we have our string message, and then we had a second parameter, or a second variable called length. And this guy was equal to the endpoint of our string minus the message, which is the memory offset. So this guy tells us what's the length of our string from here to the end of string character. All right, so this guy automatically gets the end of string put onto it when we define that data byte, and this calculates the space in between the base address of message and where that end of string is. It gives us the length of the string in terms of bytes. All right. So that's what this offset is doing. So we're moving into DX, effectively the length of our string. Okay. Then we're interrupting the CPU. So this is DOS assembly. So this is our DOS interrupt. All right. So for DOS, when we write something to the screen, we have to give it our, and actually I'm interested in something just real quick. Don't expect that this will. I just want to know if this emulator will emulate Linux assembly or not. I don't think it will. I think it'll do DOS. Yeah. All right. So, and I'm just going to leave add nums in here. We saw last time that once we get to the end of this, it's going to spill off because these guys are just linear in nature. Even though we had a call that called down to our add nums, once we hit here, it just continues on. So if we want to get past the end of these things, we're going to have to do a jump to some label or something like that. Not important for us right now. So we move into AH, the instruction that we want to do. This is the DOS operating system command for write crap to screen. All right, that's what that guy is. This is what am I writing to screen? All right, so we're writing the offset of message. So this is going to say go to base address of message and write as far as message goes until we hit the terminating character. All right, and you could have found different examples of DOS hello world. I think this was a little different than the one we originally had in class. Doesn't necessarily matter. In fact, actually, if I say new com template, actually no, let's see. Here, examples, hello world. This does with all the pops, right? I hate that one. All right, so the Linux version we looked at required 4 things. So we moved the length of something into a register, the message itself into a register. The DOS version of this handles both of these inside of one line because it deals with the offset of our string. All right, so those two get compressed into a single instruction for the DOS version of this. We also, for Linux, had to move the file descriptor where we are writing it to into another register. We don't need that in DOS because it's assumed that we're writing something into the screen. Here's our system call. So we do need this guy. So in Linux, the system call was 4. In DOS, the system call is 9. That's the DOS thing for write crap to screen. All right. So what do we need to make this work? In DOS, it's what do I want to do? I want to write crap to the screen. What do you want to write? I want to write everything from message, base address, to its offset to the end, which is the end of the string. Then we interrupt the CPU. In Linux, that's the command to interrupt. That's the base address of it. In DOS, it's this guy. All right, so that interrupts the CPU. And then here's them going ahead and exiting out of the program. So 4 is the function to exit. So that'll terminate the program, which will keep us from getting down here if we do a call. So I mentioned a few minutes ago you can do a jump. We could throw a label down here at the very end that says end of program or something like that. Whenever we want the program to naturally terminate, we can just jump to that label and then let it finish. Otherwise, we can actually call the DOS operating systems, kill this program command. So we move 4 into AH, same exact place that we moved the 9 into before. So that AH in a 8086, so it's an 8-bit CPU. So we move the command into AH instead of EAX for a 32-bit processor in our more modern example. So we use AH again down here to say I'm moving my command into AH, and then AL didn't actually take a parameter, you're just zeroing out the register, and then you interrupt it and go back. But we don't even need this second part if we don't want. Okay, we'll leave it in there for right now. That way the program will end and this stuff doesn't impact anything. Go ahead.
Can you explain to me why there's interrupts in there? What are they for exactly?
The interrupts. So this is being done by the processor one line at a time. Mm-hmm. All right. So we're staging some values inside of these various registers, and those values, if you remember when we discussed this Linux example here, basically doing the same stuff. We had 4 pieces of information that we staged into various registers in preparation for telling the operating system to take over. This interrupt here, so this is the Linux version of the interrupt. What we have in the other thing is the DOS version of the interrupt. That's why the number after it's just different. This calls upon the kernel, which is the actual DOS operating system or the Linux operating system, and that guy knows to immediately look inside of EAX for this guy, or in our example, it knows to look immediately inside of AH. It's like the rules of that system call. It knows to look in AH to find out what is it that this dude wants to do. It finds the write crap to the screen system call in there and says, oh, okay. So now I need to know what he wants to write. The write crap to the screen system call for DOS requires one input. It needs to know the offset for the length of the message you want to write. So you're giving it, this will give me a memory address right there using offset. So this is similar, well, it's equivalent to what we did over here, where we actually stored that inside of a variable called length. All right, so in Linux, we had to stage 4 different values in here. How long is the string? What is the string? So this is base address. This is offset off that base address. That's what those 2 lines are. This is what we're writing it out to. So that's system out is that file descriptor. This is what are we doing? What command are we doing? So as soon as we interrupt, which gives control to the operating system, the kernel, it immediately checks EAX in this case, or AH in our 8086, a much older architecture. It immediately checks that guy to find out what is it that you want to do. I want to do a system write. Okay? Because of that, it knows that you have 3 parameters that you had to stage in very specific places. One of them will be found in EBX, and the meaning of that guy will be what is your, where are you writing it out to? Are you writing out to the screen? Are you writing out to a file? What are you writing it out to? ECX should hold the base address of the message you are writing. EDX should hold the length, the offset from that base address that you keep finding bytes for writing it out. Okay, so the Linux system call for syswrite requires 3 parameters. So we stage all of our values there. So it doesn't matter what order we do these 4 lines in, as long as they're all set before we interrupt, passing it over to the operating system. Same thing is happening over here. We're staging some stuff. It didn't matter what order we do those two lines in. This is what are we going to do? This is the one parameter that guy needs. Because DOS makes the assumption that the write thing is writing to the screen. I believe actually DOS will allow you to put some, I think it's actually a different system call to write to a different file descriptor, and that's because DOS, for those of you who had the 450 class last semester, we talked about Posix operating systems. So Posix operating systems are operating systems where everything is a file. Linux is one of those, DOS is not. All right, so with Linux, the reason we had to give it more parameters, the reason we had to tell it what file descriptor to write this guy to, is it didn't just default to the output, the screen. We had to say, what is the ID of the file we want to write this out to in a Posix operating system. In DOS, the default is the screen. All right, so we didn't have to give it that parameter. So this is what we want to do. This is all the information it needs in order to be able to do it. Then we say, operating system, she's all yours. So that interrupts our program here, turning I/O. So if you've had the operating systems class, this interrupts the CPU, so the CPU isn't just sitting there waiting, and it lets the operating system take over I/O. Operating system immediately looks at AH, says, oh, this is what I'm doing. It knows it'll find its inputs it needs inside of DX. So those are the important things we need to pull out of this, is that AH is the command. DX is the value we're writing. All right? And then this says, actually do it. And then the second part here is the function to quit our program. So 4C is the exit command. That's in hex. So 4C hex is the exit command if we were to look at the DOS system calls. And then We move into AL00, which must be the parameter to actually kill the program. This is probably an error code. And then we call the operating system again, and what that does is it terminates this process on the CPU. In our world here, these 3 lines would be optional. All they do is keep us from running into our adnums procedure over here, because this makes the program immediately end. Takes it off the CPU and that kind of stuff. All right, so we'll leave it in for right now. That way we don't have to deal with what happens when we get off the end of this. So let's go ahead and run this, and we should see hello world print to the screen. So let's emulate. Oh, I got rid of those parameters. So, so why don't we just get rid of it? Good enough. It was complaining because I took those variables out and was still trying to use them below. All right, so I'm actually just going to hit play on this guy to run. Rubro. There's hello world. What was all this crap? The offset was bad. Need to kill this. That guy looks fine. Sis write command. Those are the let's do the offset of the message. It's picking up memory that we didn't use. I guess I won't use this to show you offset then. So we'll use the built-in. Hello world, life will go on. So I'll go to examples, hello world.
Take stack off of the program.
Because that's bumping into the offset?
I think that's what it's doing. I was having that issue with my homework until I took stack off.
We need it. Well, the thing is, ours needed stack.
Because you are pushing stuff onto the stack, unless you put it into variables. Yeah. The issue here is
we need the 180.
yeah. The issue here is that we're that offset is bridging because of the order we have the stuff in. I have a feeling that if we move the data below after our code segment, they won't interrupt each other. This offset is remember each of these segments have a base address. The DS register holds the base address of the data segment. The CS register holds the base address of the code segment. We are seeing when we write this, let me just undo this here. Do it again. This is the base address of the stack. Okay, so we have this whole address space that we're working with here. When I move into, and let's actually walk through this. We'll see what gets loaded into message here, and I'm just going to actually do this. I'm going to say move. Yeah, we're not using. I'm going to move into BX message. Okay, so we're going to see the actual base address of this variable message here, and then we're going to see the offset from that for DX. So we'll be able to see those two values, even though the command 9H doesn't rely on us giving anything in BX. We just want to see both of those values.
You got an X where V should be in move.
Oh, thank you. That's a data byte, so we'll do BL. All right. So we'll move into AH, the value 9. That's the call we're going to have. We'll move into DX, so our full 16-bit register DX. We'll move into it the offset of message. Okay, so that's 121 hex. Okay. Then we're going to move into BL, the base address of message. So that's CD. So that means message starts at memory address CD, and it keeps going to memory address 121 off of that. Okay? And we're taking steps of size. This is ASCII, right? So 121 in 121 hex is what in decimal? .121 hex to decimal. We have 1 times 1's place plus 2 times the 16's place plus 1 times the 256 place. So this is 1 plus 32 plus 256, which is 289. So that's 289 decimal. Okay, 289 divided by 8, because this is ASCII, right? Is 36 and some change. So it's going to be that's overflow there. That's where all our extra spaces are coming from, because it's doing an offset and it's going. I mean, hello world only has what, 11 things in it or something like that, and it's trying to give me 36 bytes because of how it's calculating the offset. Not the end of the world, but that's the deal. And it's because the simulator, well, it's not a simulator, it's an emulator. The emulator puts all these guys in fake memory right next to each other. So doesn't really hurt us in this case, except the output just looks funky. So this is just showing us what all those, what it's interpreting junk memory as characters. And it's just getting a whole bunch of empty crap. All right, but we have a hello world at the end of it, and that'll be, let's just say, good enough for our example here. All right, so let me get rid of this so we can keep this guy as simple as possible. All right, so what we need to happen here is we need to create a procedure for writing crap to the screen. That's what we're trying to accomplish. That way we don't have to remember that the DOS command for writing crap to the screen is command 9. Not that much to remember, but wouldn't it be nice if we could just, I want to display something to the screen, let's call my procedure called display to screen. All right, so we're going to write a procedure down here called display to screen. This guy will be a proc, and later on we'll NP display to screen. All right, so this is going to be our procedure. And we'll go ahead and inside here we'll move AH09H, because that's the very first thing we need to do to print something to the screen. Then what do? Well, we need to move into DX the offset of our message. Okay, and the issue here is that this offset is from the screw up here is that this emulator bases this code address as whatever's in CS. So this offset of where this variable is, which actually lives inside of the data segment, is an offset not from the beginning of message, but from the beginning of the code segment to wherever this message is. Okay? It's because this is an emulator and not an actual assembler, just how it's decided to organize its fake memory. Okay, so that's why their example in here specifically deals with it as an array. And we're going to talk about arrays today because then they can control where the beginning and end is without relying on the position of those different registers. But display to the screen does what? It lets the operating system, well, it lets AH know the number 9, which effectively we know is going to let the operating system know what we'd like it to do. All right, then the next thing we need to do is we need to move into DX the value. Okay, we'll keep with our example here. So it's going to be the offset of some value. So why don't we just leave it as offset of message for a second, and then we can look at some of the things we can do. Then we call int 21h. And what does this procedure do? It displays to the screen, among some other things, what's inside of message. So whatever we put in message, this will display that to the screen. Make sense? All right. So come back up here. We can.
Do you not have to put a return in there?
Oh, you do. Thank you. Just RET, right? And that will take the value off the top of the stack. I mean, we could have gotten away without doing it, but then we wouldn't have gone back up here, right? So if you don't have the return there, we won't use that value from the top of the stack that we talked about last class, which won't return us back to our blah procedure up here and let us keep going. So we're going to go ahead and take these lines out of here. Let's just get rid of all these for right now. All right, and we'll go ahead and just let it do hello world first, then we'll play with this a little bit. So we're going to say call display to screen. And then we'll just do like a move AX comma 5 or something like that, just showing that we return to our code here. So what return does is it pops off the stack back to the next line to be executed. So after we do our display, it'll return to here. Go ahead and run this. Step through it. So there's our moving into AH number 9. Then moving into DX, our offset from our what should be our base address of message, but is actually the base address off of the beginning of our CS pointer. Then interrupt. Okay, so notice we're down here in display to screen. And notice here inside of our stack, the top of our stack is our pointer back to where in memory we should pick up, which is this position here. And that's what we talked about last class. So we'll interrupt, step through that. There's our hello world. Okay, now it's even actually worse because now it's also going everything up to the end of the subsegment that it got when we changed the control. We're even farther away from the beginning of the code segment now. So it's our ugliness here is exaggerated. Whatever the default value in those memory addresses must translate into it probably isn't an ASCII T. My guess is it's something else that if you've ever tried to use a Java program to go through all the ASCII characters or all the Unicode characters, for like a high percentage of them, it just shows question marks because it doesn't know what else to do with it. So it's probably from that Java term or the DOS terminal here, what it thinks is the default. I don't know what the heck you're trying to make me do. Okay.
How come you were able to run the program without the 4H after the call?
That 4H thing,
Yeah.
you mean the second one?
Yeah.
That's a second system call. So we're doing syswrite first, The second one is Sis Exit, means make our program end. Well, in this case, we kind of want to return control of our program so we can keep going. Because we might, for example, want to prompt the user to enter something. Please enter a value. So you prompt the user, well, you don't want your program to end. You kind of want to come back so you can actually read in that something. See what I'm saying? If your program ends, then you're done. You prompted them for some information, and then your program literally ended with that second system call. So every system call dictates the operating system that we want to do something. So right now we're doing one system call that says display crap to the screen. That second system call was make the program end. We're done. Do not pass go. Okay, everything's done. So that's why we took it out, so we would be able to come back to our move AX up here.
If there wasn't the move AX, could you put the forward stage in there?
If we were legitimately done, we could. If we didn't, though, so in this case we didn't, forget whether or not we have the move AX thing here. What it's going to do is it just keeps going linearly. So it's going to go down to our procedure down here and do it again.
Oh, yeah.
Yeah, so we have a couple of options. We can either put a jump command in there to just hop over this. So at the very, very, very end of your program, you might have like I'm done label or something like that, and just jump to that label whenever we don't want to do any extra crap. Or we can rely on the operating system to bail us out. That's what the 4 is. We're saying, DOS, we're done. Do your kill this program thing. All right. So let's see. Did anybody who did this way figure out a hack to make the addresses not show all the extra crap? Or did you all do it the array way? Or did you do it a completely different way? Or did you just not do it? Because it would be nice not to have these extra crap here. So how anybody get it to display without the extra stuff?
We did it this way, and it didn't display with all the crap.
And you used the same model, or did you use Tiny?
We might have used
Guess I could just try it while you're. It's possible since the Tiny model builds a .com that it doesn't
we use small.
use small. Okay, so you use small like this, and you still had your stack.
We used the org 100H. We found that. I don't know why.
Well, yeah, that's the default. Actually, that's the default for Tiny,
Okay.
but unimportant. So you did that instead of the stack.
Yeah.
Okay, so this is how you let them know about your stack pointer.
Yeah.
And then the rest of this is the same?
Yeah.
All right. Yeah. And it did hello world twice because we didn't kick out of it. It just kept going down. Yeah, so that's weird. So the dot stack pointer.
Why don't you put a return in your main?
I can.
Okay.
Yeah. That would keep it from doing it as well. Yeah, so what he's suggesting is if I just do, it's going to yell at me. Kind of hate that it won't just let me type stuff. That if I do this, I don't have to jump. That's effectively relying on the this program ending itself rather than making the operating system end it. Now, so operating off that, why might that be a bad idea? A small example like this, it probably wouldn't be. But what is the difference between us having this procedure end, which makes everything end, versus, and let's just run this real quick. Ran, ended. What's the difference between us doing this as opposed to relying on DOS to kill our program?
Probably just had where it just keeps going, so you can things run that you don't necessarily want to run.
Well, but putting a return there or putting the end program DOS system call will ultimately give us this exact same result. The thing that won't give us this result is if we leave both of those out, right? And just say keep trucking until we just hit the end of your instruction set, your code segment. So what's the job of an operating system? This kind of goes hand in hand with what we're talking about here, of this relationship between our assembly code and the operating system on which it was built to run. When we put a return here, as Curcio said we should do, this makes our blah procedure end. Our blah procedure was the very first procedure inside of code, so it's effectively our main method. I think we had it called main last time, and then we changed it to blah just to proof that it's the first thing it bumped into. In that case, we don't go down here because we're telling the very first thing, the very place that control started in our code segment, we're telling it to finish, to return, to end. It's going to push something onto the stack in case there are more lines, but we run out of crap to do. So from our perspective, this code ends, right? Program's done. Similarly, if we do the DOS system call for 4C, which is exit, kill program, that's relying on the operating system itself to kill off this program. So we can just run out of things to do naturally, die a natural death, if you will, versus having the operating system execute us. Why might having the operating system execute us, as in kill us, be better? Sounds way worse, right? Why might that be better? You got to think about the job of the operating system. Go ahead.
Like the job of the operating system is to manage programs and applications, so that's what it does.
Okay. What does it mean to manage applications?
Like start them, stop them, how much memory that application gets.
Okay, so there's more to running a program on the CPU than what we're doing here, right? We're kind of reliant on this operating system to somehow magically load our application onto the CPU and actually execute it. And when we were doing this out there at the linker, we actually built an executable, right? When we were looking at this on Linux, and then we did the /hello or whatever we called it to run that program. In that case, we were relying on the operating system on Cloud 9, which was Linux. We were relying on that operating system to actually run our program. It was the operating system that started that program. So we might say, well, if it's the operating system started it, shouldn't the operating system end it? Oh, that's fine. It's easy enough to say that, but the answer might be why? Well, how many programs do we have running on our CPU at once? Potentially several. And part of the job of the operating system is to manage all those guys. So if you have 10 jobs running on the operating system at once, we talked about when you had the operating systems class, some of you are in that now, but you'll talk about something called context switching, which means that as you're walking through your code here, you might get through this line and this line and this line and this line, and then your time on the CPU is up. So they need to copy all those registers to some place so that it can remember where you left off. So the next time this guy gets put onto the CPU, it can pick up right where it left off and go to here, then here, whatever. Does that make sense? So there is a level of management that happens on the operating system where it would be nice of us, probably smart of us, to actually make DOS aware that we want this program to be finished. You no longer have to babysit me. Go ahead and take me off the queue, kill me off, whatever it is that you do to take me off of your agenda, okay, which may be something simple, may be quite a bit of paperwork that the operating system has to do to free up the memory that used to be associated with this guy, take him out of the waiting for next instruction queue, all this stuff. If we tell the operating system to do it, then the operating system doesn't have like these leftover chunks of our program that's laying there because we just ended it with kind of willy-nilly. Now, having said that, most modern operating systems, including DOS, are going to have facilities for programs that end on their own. Kind of like our equivalent of automatic garbage collection, where the operating system will notice that, oh, I'm about to load this guy onto the CPU, but his next instruction pointer, IP, currently points to an address that is off the end of the code segment. Therefore, this guy must be done. Not a big deal, but that takes a little bit of time, doesn't it? But then again, you might say, well, interrupting the CPU and having the guy kill it off, that takes a little bit of time too. So maybe it's a tie. But good programming practice might be, if the operating system started the guy, let the operating system know that he can clean up the memory, do what. That way it's ending on your own terms, as opposed to you just kill it off and leave a mess behind you, something like that. Okay, so does this make sense? How we can move stuff that is less scary on DOS than it is on Linux, because Linux uses a single system write command. Since everything is a file in Linux, it uses that single system write system call to do lots. It's the same thing writing to a file versus writing to the screen versus writing to a USB hard drive, external disk, something like that. All right, so we can move that into a command. Same thing, what if we want to 8086 DOS read input. This would be good enough. Don't like that version. I want something simpler. We want to look at loops today as well. All right, so this is the system call for capturing a string. This is what we're going to read it into. Okay, that should do it for us. So, so this is read string from user. Okay, and this guy is going to be a proc, and then we'll have an end p read string from user. All right, and then I'll paste. All right, so we're using the same two registers as we did for writing something to the screen. We're using AH for the command we want to do, the system call, DOS system call we want to do, and then DX holds our data. All right, and in this case, it holds the data that is our buffer, the array, if you will, of what we're reading the value into. So up here, they created a buffer that is a data byte that allows up to 25 characters. So that'll be 0 to, this will be, the last one is for that, the $ string termination character. It's a default on there in DOS. So this will allow us to read something up to 25 characters. Fine. So we'll roll with that for a second. So up here, we'll create, buff is just a variable name. A lot of times they're called buffers. You maybe have seen this in some Java source code before when you have to read something into an array. You might pass a buffer in, which is maybe a 1024 byte array, and it fills it in 1024 bytes at a time, something like that. So this is a place to put stuff. All right, this guy is going to be a data byte 26, so that makes it an empty array for us right now. Okay, that's contiguous memory for holding 25 bytes terminated by the string termination character. Make sense? And we know that string termination character is going to be there because we're using DOS, and this is the DOS read crap from user thing, which will read everything in and then plop a string termination on the end of it, because that's what DOS does. DOS uses that guy as its string termination, so when it reads in a string, it'll use that. So there's going to be a different command for reading in an int, but we'll start with the string thing here. All right, so we move into AH, 0A, which is the system call in DOS for, I should look up somewhere if we have a list of all the system calls just for our 8086 emulator. This is the system call for read a string in from the user. Then we tell it the offset of our buffer where we're reading it into. And DOS, then we interrupt it, and the DOS's system call goes and does its magic, and it reads in our string until we press enter. And we can read up to 25 characters, but what if we only put in 3? It's going to put that termination symbol at the end of 3. Make sense? So it tells us where our string ends. All right. So we're reading that into our buffer. Then we'll end this guy. So let's go ahead. We're going to get rid of this. So let's read something in from the user, and then let's write something out. Let's echo it back to the user. Okay, so the very first thing we'll do is we will call read string from user. So we'll call that function. We need to make sure this guy returns. So this does the read crap. It moves into DX, the container for catching the string that we want to read. Then we interrupt the CPU, letting DOS take over. DOS looks in AH and says, oh, what are we doing? Oh, we're reading in a string. Great. It goes and does its magic read string in from user thingy, which is going to default to the keyboard. If this was in Linux, we would have had to give it more parameters for where are we reading this in, because it doesn't know if we're reading in from the standard input or reading in from a file. Because it would do file I/O with the same single command, where DOS separates those out, where file I/O is different than reading stuff in from the keyboard or displaying stuff as a string. Because DOS is not a Posix operating system, therefore it doesn't treat everything identically as a file. Some things are files, some things are not files in DOS. Just a difference between the operating systems. So we're going to read in a string. Okay, where do you want me to read it? I want you to read it into this memory address. Okay, the offset of wherever buffer is off of the base address of our code segment. Okay? And then tell the CPU to go, or the operating system to do this. So when this is said and done, buff should hold our value in system memory, not in a register, right? Buff is a variable that's held in memory, system RAM. So we'll read a string into buff, but when we display to the screen, display to screen automatically uses message. Well, I could move into message the value of buff. So let's go up here. Use the move command, and we'll say message is the destination, buff is the source. So we're moving one memory location into another memory location. Is that allowed? Go and look at our 8086 character set. Is that this guy? And let's look at move. We can move memory into a register, register into memory, register into register, immediate into memory, immediate into a register. These are stack pointer registers. So nowhere in here can we do memory to memory. So if I want to accomplish that, I need to first move it into a register, then move the register into memory. So I'd have to, for example, move AX, comma, buff, then move into message AX. Okay, so I'm moving the base address of buff into AX. Then I'm moving the base address, I'm moving AX, which effectively was the base address of buff, into message. Now when I call display to screen, it's displaying whatever's currently in message. Let's go ahead and run this. Oh, one's 16-bit, one's an 8-bit. Oh, because this guy's a data byte. So I need to move into, doesn't matter if I do AH or AL. Buff, this guy right here, was a data byte. So it's 8 bits. So I need to use an 8-bit register. Remember, our move command requires both of these to be the same size. So AH is the high side of the 16-bit register AX. So this guy's 8 bits in and of himself. So I'm moving this 8-bit address into this 8-bit bucket. Then I'm moving this 8-bit bucket into this variable capable of holding an 8-bit value, base address. All right. So I'm going to go ahead and just hit run. Okay, so it's waiting for us. We didn't prompt. It's waiting for us to type something. So I'll do LOL and press enter. Okay. Now it's doing hello world. This is my output. We get a little weird symbol here. So now let's step through this. We want to see what happens to AH. All right, so we'll step. So we're going to call our read string from the user. It's going to do that. Then it's going to wait for some input. Can I actually get it to, there we go. So we'll do LOL. Read that in. And we'll return. Now, that LOL should have been read into our value for buff. Do they let us see our variables? They do. So buff is holding a value of 1AH. Okay, so 1A is the base address in memory of that variable called buff. Okay, it's the actual value is a pointer. All right, so now we're going to move into AH buff. So there's AH right there. So that's our, did I hit it already? Oh, that's the next line. There we go. So AH is currently 0B, but I tried to move the value of buff into that. Buff holds the value 1AH, and when I moved it into AH, I got 0B from it. So right off the bat, we got a weird disconnect, right? Then I'll move into message, the value of AH. AH is 0B. There's message, 0B. Okay, fine. Makes decent enough sense. We don't know where that 0B came from. It didn't seem to match up with our 1AH, but at least this call worked fine. Then we call display to screen. This comes down here. We move into AH, our value 9. It's okay, we can overwrite AH now because we preserved the value inside of a variable, okay, inside of a variable called message. Step again, there's our offset of message into DX. So DX is right here, 102. Then we interrupt, and this was the LOL that we originally entered in. So that's not part of this, this answer. Actually, it is part of this answer because this is 2 separate screens. That's good. So I'm just going to run this again. So waiting for input, I'll do LOL, and there's my output. So the LOL was already there. Okay, so this was not part of our output. The actual output from our display to screen or display to user was this guy right here, followed by LO world. Why do you think we got this? Let's look at the original base address of message. So we'll emulate this. Let's look at our variables. Okay, so remember, when we first load our program here, the data segment gets read in initially. And this data segment created a variable called message that's of type data byte, and we put in there the string literal hello world. So message has a base address of 48H. Right, that's what that guy has in it. We step through this, read string from the user. Let's just get to that point. Put in our LOL, press enter, and then I'll go ahead and close this. It'll reopen here when we're done. We return, come back up here. We know right now that our buffer holds 1AH. And actually, I want to reload this just so we can look at what the buffer had in it initially. So I'll step over our data segment. Okay, so data has been read in. Let's look at our vars before we've done anything to them. Buff has a base address of 1AH. This guy's an array, right? We've advertised this guy as an array. It's a variable named buff of type data byte, and it can hold 26 of those dudes. So what this does is it grabs 26 bytes of contiguous memory. Okay? The very last of which is represented by that $, which is the string termination character in DOS. All right, so we have 26 bytes in a row of contiguous memory. We weren't reliant on how we got that. All we know is the base address of that guy is 1AH. All right, that's its base address. So we step. We're reading some string in from the user. I type LOL in. Oh, I'm sorry. Close this. Buff is still 1AH because that's its base address. If I were to look at buff at bucket 0, for example, we should have the L. Buff at bucket 1, we should have the O, so on and so forth. When I move into AH, the value of buff I get a 0B. So that's an 11, decimal 11. Okay. Where did the B come from? This comes down to how arrays work, and we've seen it in Java before. We know that the value of buff is 1AH. When I move into AH, which is an 8-bit register, the value of buff, I'm moving into it the base address plus 0 times the size of whatever's there, which is a byte. This is the very first byte of buff, which in our world should be we presume it should be an L, because that's what we typed in, right? But when we went to print this out, so we moved that into AH, and then we moved AH into message. So we saw that these two guys matched up. There's our 0B. So this holds not the address of what we want to display. Instead, it holds it's going to be treated as a base address. The reality is it's holding the first character of something off the base offset of buff. Keeping in mind that buff was just random memory because we didn't define it to be anything initially. Okay? So, step through, we'll go to print stuff out, blah, blah, blah. Run this. When it printed out, this was the first thing it printed out. That's what we moved into message. We moved into message that value, whatever is being displayed as a square. So similar to what we were talking about before, it's this terminal's interpretation of what that value was. And then it's writing out the rest of the crap based off the offset of that guy until it finally hit a termination character. So we got hello world, because that's what was inside of our memory. What if we do this? What if we change our display to screen to do this off of buff rather than off of message? Which then means we don't have to do all of this workaround stuff up here to move buff around. We definitely saw that things went south right there, didn't we? When we tried to move the value of buff into AH, we got a value that was unexpected. Kill this here. So we'll read from the user, display to the screen, using the exact same variable that we read in from the user and that we displayed to the screen. So message might as well not exist in our program right now. Okay, let's go ahead and run this. I'm just going to run it outright. LOL. Just trying to print out whatever buff was.
Was buff our input again?
It was, which should hold the value that was the result of reading something in from the user. Go back to this example here. So notice there's 3 variables here. So we have buff. Buff is number of characters allowed, but associated with this one guy, we have some other things. All right, this is the number of characters. That's going to be the length of that string, length of that array, and then we're defaulting it to be filled up with 26 zeros to begin with. So the dupe command gives us the ability to fill up an initial array. We're getting contiguous memory, 26 buckets of contiguous memory. Currently, the values of those are whatever they used to be. It could be zeros, it could be what was ever left over from the last time that memory was used by the operating system, whatever. Okay, it's filled up with stuff. This guarantees that it's filled up with zeros. Because keep in mind that some of that stuff that was there, and we saw a result of that stuff when we saw the little square, some of that stuff could be string termination characters, it could be all sorts of stuff that gets interpreted by DOS in a way that we didn't necessarily want. All right, so when we create our buff here, we're creating it as a data byte of 26. We don't know how many characters are currently going to be in there. And we're going to go ahead and fill out the memory that we grabbed with 26 zeros. Steal this guy. All right, so buff will be 26 data bytes. So this is going to be the contiguous address space. We don't know how much stuff is going to ultimately go in there. And we want it to start off as 26 zeros. Here's us capturing a string from the user. So we already have this in there. This is DOS's capture string. Starting at the offset of buff, read it in. Now, notice what they're doing down here, and we'll look at this in more detail next time, but we've advertised that this guy right here is the DOS string termination symbol, right? You can cut a string short by artificially inserting a string termination symbol somewhere in the middle of your string. Make sense? All right, so we'll look at that, but let's go back in here. So now we're more fully defining our array here. That is, how much memory do you need? How long is the current string? We don't have a default value for that. That's why we're putting a question mark. We looked at the question mark for default values last time. And then this dupe command, which is new, this says duplicate this value this many times. All right, so we're going to fill that up with a bunch of zeros. Go ahead and emulate this. Oh, I got to drag this out of the way. That's it. There's my LOL. Let's see what it did when we kill this, run this, and watch what happens to our variable. So single step, read from user. Let's just go ahead and get that value in, LOL. Step, return back. So we're about to call it to display screen. Our buff still has its base address. Doesn't matter what message is. When we go to display this, we're giving it the offset of buff. But we don't really want the offset of buff. We want whatever this portion of buff was. How long was it? What did the DOS system command for reading a string and set that value to? Does that make sense? All right, so we'll pick up here next time. What I do want you to do is I want you to read something in the book in preparation for a quiz, potentially a quiz. And what I want to look at, have we read 3.3 and 3.4 yet for division and multiplication? So we've just done addition and subtraction.
We haven't done 3 yet.
Yeah, okay, so you're sitting at
2.8, 2.8.
okay, 2 9's a waste. We're not going to look at that. MIPS addressing. We're going to talk about synchronization next time. And we're talking about arrays. Let's go ahead, just to jump ahead a little bit, read 3.1 through 3.4. No exercises associated with it, but be prepared for a quiz dealing with this. And realistically, the quiz will focus on multiplication and division. All right, because we've already pretty much talked about addition and subtraction. Okay, I will see everybody on Thursday.